Resin printing machines, again, there's a range of resin printing machines, both from 3D Systems and also from an Israeli company called Objet. So there's no C in that title over there. And that prints a resin but cures it with a UV light. So every time you print your material down, you UV cure it. The support material is a slightly modified resin. Probably not wonderful on material utilisation. Another process is the factory machine. Some people doubt, is it a rapid manufacturing machine? Well, it can be. I think it potentially could be, because it's using a projection system to project a pattern of light onto this. You can see here there's an actual platform that's upside down, so the part grows upwards that way, and you feed more resin into this shallow vat as time goes on. So it's projecting an image, not dissimilar to the image you can see on the screen. You know, it's using a similar projection system to the one up there. It cures an entire layer one at a time, and it allows you to build multiple parts, very complex parts quickly. And there's a whole range now of materials which are being developed. And I think if you're into casting jewellery, then it is a rapid manufacturing machine. If you're into making hearing aid shells for customised hearing aids, then yes, it's a rapid manufacturing machine. They show examples also larger parts. I will caution against this. My experience with the factory process is it's great at small parts, big parts, it's a disaster. Okay, but don't tell Envision Tech I said that, but I don't rate it as a way of making big parts. We'll now quickly talk about the process being developed within the custom fit process. You know, what we're trying to do is migrate from standard RP processes to faster, better materials, functional grading to satisfy the requirements of rapid manufacturing. And the first process was actually developed by Sinter. And so Klaus knows more about this than I do. And it's a process of metal printing. And the process works by taking a metallic powder and electrostatically printing it or picking it up onto a plate. And then, so you can see there, that's the powder. It's picked up onto this plate. That plate is actually a punch that pushes down into a furnace and fuses that layer in a few seconds. So there's your printed layer, there's the punch, and it goes into the furnace. It's an amazing process. I mean, it's a furnace, a little localised furnace. Door whips open, in it goes, fuses, comes out, the door closes again. And it's an inert atmosphere in there, so you don't get oxidation. And you can produce a part that's a combination of, is this iron?
Iron and copper.
Iron and copper. You name a part process that can do that. Not many, is there? That can do that combination. We've got a solution to a problem we have to find, I think. This is the video. I've been told how to do this. And there's probably sound. You all see that? That's the punch, and in it goes. It would be fair to say the process needs a little speeding up, but the principle is there.
This is a demonstration.
That's a demonstration. This is not slowed down. This is real time. But the elements are all mechanical elements that can be quickly speeded up and then closed again. So that's a layer at a time. There's lots of discussions about whether it's better than laser sintering. It's a different approach, and it allows you to get functional grading. Escape. Okay, so that's the sort of things you can do. And there's been some materials research, and Klaus will explain a bit more about the material, but things like cobalt, chrome, titanium, iron, copper have the materials which have been tested, and also this functional grading from 100% titanium to 100% cobalt chrome. You know, this is doing something we've talked about, but actually now seeing it in real life. High viscosity inkjet printing from TNO. It was an organisation that Youngman used to work for. Very impressive machine. What it does, it uses the continuous inkjet printing process, but with very, very viscous materials. One thing you can, and that's the critical issue, that's a critical part of the patent which they have. It allows you, when you've printed this viscous UV resin, to then cure it to make samples. For those that are not familiar with continuous inkjet printing, what you can do is you can charge the droplets and steer them. It's a faster process than what's called drop-on-demand, which is a standard, desktop printing system. But it is quite technical. It's not easy. That's the machine. Hopefully it will wish forwards. Yeah, right. Okay, that is real time. And so that carries going backwards and forwards, going under 3 inkjet heads. And then it's curing and then going back again. So this is suffers from the problem being too fast. You actually can't see what's going on. But there's a stream of droplets from every print head. The reason why I've got multiple print heads is we want to be able to put 2 bill materials down and the support material. So that's been developed within the custom fit project. And so the critical issue is how they deal with this very viscous material. And they've got their own control software. That's the stream of droplets coming out of the head and how they steer it. As I say, it's not for the faint-hearted. Drop on demand is fairly simple. You squeeze a droplet and it flies and it hits the substrate. This allows you to do some fairly strange things mid-flight. Not quite really. It's moving across us about each time. So clearly the guys at TNO can make complex bits of kit. And that's the samples that are coming out of it. As I said, the key is the process control. It's one thing eventually squirt the material out quickly, but get it in the right place. And this perhaps doesn't look very much to you guys, but this is like landing a person on the moon in terms of rapid prototyping. Okay, I think that's hopefully it. Especially my escape problem, it's just right. And those are some of the initial results. So not huge, but okay. At least they look like the thing that they are. I think they did the CAD first, then made the models. They didn't make the models, then tried to get the CAD to match the models. So I trust them. There's no cheating going on here at all. So. And as you've seen before, the ability to combine materials is there. And again, we have to develop the applications, but it's a unique capability of this machine. The last process is one we're developing at Montfort University in conjunction with our partners at MCP and CTG. And it's plastic powder printing. And it's based on laser printing. And the idea is you have a laser printer, you effectively print the surface down, and then you fuse the whole area with an infrared radiant heater. So it potentially could be quite fast.